but I will show you the code directly on the other documents we have on it. It's stuff which some stuff it's an early prototyping phase. Some stuff will be released with the next version, which is coming up. So I'll just pick up the few highlights we have in our pipeline. The first one would be a new Spring integration. So let me share my screen. Right. So I'll keep the chat open. If you have questions, we can make it a bit more interactive. All right. So the new Spring integration will contain some really nice features. Some of them we try to move them over to different frameworks as well. The first is the storage can be now injected with by configuration, and the root type can be configured. So all the creation of the storage manager or the default instance of the root object will be done by the framework itself. So you just define the type of your root type in the Spring configuration, in the application configuration. And for example, you can configure the configuration for the storage itself. So the storage will be written into the choke storage directory here, and the root will be used for the storage. And every time you use the storage, you can just use, for example, the constructor injection here, and you don't have to worry where the storage manager comes from. It will be managed by Spring as a component in the background or as a bean. So this is a simple case where you have one storage manager for your application and one root. If you want to use multiple storage manager, you can use qualifiers for that, like you used to in different Spring features. And so you can manage multiple storages and root types for one Spring application. All right. So, and the bigger feature we want to provide in different frameworks as well in the future is an enhancement of the logging situation we got with Eclipse Store, because you're operating on a shared object graph, meaning the concurrency or the concurrent access to the object graph has to be handled by the application. In a demo before, I showed you how it can be done, for example, with reentrant logs. It's doable, but it pollutes the code a bit because you have to write a wrapper around basically every method which accesses the object graph. And so we thought, since we are in a CDI environment, we could do it with annotations. With in this case, we're doing it with aspects, aspect J in Spring Boot. And now all you have to do is write read and write annotations on top of your methods, and the code for the reentrant logs will be generated in a background with aspect for J. And so I think this is the shortest way possible to tell the frameworks, hey, you have to read and write log here. And the thing where you have to know what method reads the object graph or write, you have to know that anyway. So the framework cannot automate it. You have to tell the framework where stuff gets written and stuff gets read. But you're the owner of your code, and you see where it's done, and you only have to simply add the write and read annotations. You can define specific types of mutex. What mutex should be used? For example, this write and read annotations use a global log. And if you want to use different log mutex, for example, you don't want to log the whole object graph, but just a single subgraph, you can use qualifiers for that as well. And so you can use different logs and achieve a more parallel access to your object graph. So this is, I guess, the most convenient way how you can handle the concurrent access on your data. And we can do it here because we are in a CDI environment. We try to port it to different frameworks, to different integrations. And then if you use Markdown, for example, or different CDI environments, you can leverage this feature as well. All right, so this is stuff we can show because it's in a more major state. What we're working on also is a Spring Data integration. It's in a very early phase right now. You cannot show a lot, but the idea is to basically have a drop-in replacement for different Spring Data implementations and use Eclipse Store as a drop-in replacement for your storage layer. But it's in a very early stage, and so I guess in the next JCON in spring we can tell more in spring or summer. All right, that's about the Spring integration or different other integrations which are coming up. So, and if you have ideas or if you say we can integrate in this and that, would be a nice enhancement. We're open for ideas. So just tell us. Best is to open issues on the GitHub repository or to write us directly or in discussions. And so we are open for ideas. Okay, so that's about the Spring integration. The next topic I want to talk about is monitoring. So let me switch my workspace here. The target was to provide more data which can be used in monitoring systems and have a look or better control about the health of your application and to see what screws you should tweak to get a better performance out of the at runtime. For example, if you should increase the housekeeping time or if the lazy references are handled properly, unloaded properly, how your memory consumption looks. So we decided to open more data for the outside. We do this with the Java management extension beans. This is supported by pretty much every monitoring framework out there. There are adapters for Java management extensions for every popular monitoring tool. So for that, I just let a small demo running in the background, which does, I guess, 150 to 200 requests per second, about, yeah, 170, 60 per second. So it reads and writes all the time. So we have some stuff going on our storage. And I can show it here with JDK Mission Control, for example. It's a tool from Oracle. It's free to use, but you can use every monitoring tool of your choice because we use the management extensions here. So let me connect to my application, and the management bean server view provides different data, which is interesting. The JDK itself provides a lot of data by default, so you can see how the heap is used, CPU usage, and so on. There's a lot of data you can extract from the JDK alone, which is interesting. And we'll see we got 150, 200 requests per second, and the processor is basically idle. So the small machine here has a lot of potential left. And now if you look at the Ambient browser, here's all the JDK stuff which is offered by default. And now the Eclipse Store beans can be used as well. For example, we look at the lazy reference manager and we want to check how much loaded lazies are there compared to how much registered, meaning basically what percentage of lazies are loaded. We can visualize these two values in a new chart. Let's call it just lazy. So we see the lazy references. We have around about 25,000 lazy references in total. And depending on the data usage, there are about 700 or 800 lazy references, 600 loaded. Depending on what parts of the object graph is used, you'll see it gets cleared from time to time by the lazy reference manager. Here was a drop, and now queries access different lazy references and they get loaded. So you can see what part of the lazies are in memory. It's an interesting thing to see. And another one is the state of the storage itself. You have the embedded storage, which offers a storage statistics accumulated over all channels. So we can see the total data length, which is the overall size of the storage itself. And we have the live data length, which is the data representing actual or current values in the storage, and the rest is just is old objects, deleted objects, or stuff the housekeeping has to clean up. And as we can see here, our usage ratio is pretty poor. Only 18% of the complete storage data is live data, and the rest is old data, which has to be cleaned up eventually. Let me add a new chart here. So we can see the live data ratio is only about a fifth or fifth of the complete storage. So what we can do with management beans as well is call actions or operations. For example, a full file check, which cleans up the storage. And here you can see it goes up to 100% for a short while. All the old stuff got cleaned out, but we have a lot of read and write operations going on. And so the ratio drops down because the old data, which should be cleaned up, accumulates pretty fast, which is a sign for us. Hey, the housekeeping has too less time to clean up properly, so we can adjust this value. So let me shut down the application, and in the configuration we just say we want to increase the housekeeping time budget. The default value is, I guess, 10 milliseconds. So let's say we give it 50 milliseconds per second to clean up and restart the application. So I guess it takes a while until the housekeeping takes effect. But this is an important figure if you see performance drop down in the application, or the storage grows indefinitely despite you're deleting a lot of data. That's a sign that the housekeeping has too less time to effectively clean up. So you have to increase the housekeeping interval. And now we can see the effect coming in slowly. The old data gets cleaned up, and eventually it will go to a more to a better level, up to about 80%, I guess, or so, in a few minutes. And this is a thing we thought shouldn't be done by the user, but by the framework. And that's the next new feature, which is coming in the next release. It is an adaptive housekeeping controller, meaning this controller dictates the time the housekeeping has to work. And if it sees that the storage doesn't get cleaned up very well, or the garbage collector doesn't go to the sweeping phase often enough to clean the storage up effectively, it will increase the time for the housekeeping process from time to time. And this does basically this what I did right now. To increase the housekeeping time budget, it will do it in the background automatically until the storage gets cleaned up, and then the housekeeping time will be decreased gradually, so it can clock in the right amount. Other vendors, I guess, would call it AI, but it's just a simple time measuring algorithm which does the setting automatically for you. And like you can see, now we increased the time for the housekeeping. We're running about 80-90% live data, and only 10-15% for the old data, which gets cleaned up effectively now from time to time. And that's how the storage should be, or the state the storage should be in. Yeah. So these are I guess the most important, or that's the most important data you can see right now in the beans we are offering. We're open for ideas again here if there's stuff you want to see in your monitoring. We can provide the data, and so you can make sure of a healthy state of your application in deployment. All right. So, and this adaptive housekeeping controller will be used by default in future releases, so you don't have to change anything in your configuration. It will use the set time as a base. So if you have configured the housekeeping already, you gave it a time budget and different settings. The adaptive one will take this settings as default, and will calculate the time based on this default settings. But you don't have to change anything in your configuration. It will be used by default. All right. So that's about monitoring. And the next one is about a new collection we're currently developing. As I showed in my demo before, a way to effectively access your data without loading it all in the memory all the time is to create segmented or cascading collections. So you put collections in collections and go through that path, and so you can pre-filter, only load a small chunk of these collections data into the RAM. But it's a bit of work you have to do on your side, meaning you have to You have to create a segmentation by yourself. And the thing is, if you use multiple collections for a faster lookup, and you add entities to these multiple collections, you have to take care about the proper way to store them all. You shouldn't forget a single collection. So you have to worry about what collection should be populated with the entities, what collection should be stored, and where to put the lazy references. It's sometimes a bit tricky. You never know how big the collections get at the beginning, so it's a bit tricky to find out where to put the lazy references and so on. And we thought we should eliminate all this trouble and provide a collection that does all this stuff for you. All right, where's my tab? And for this, we came up with a concept. We call it internally Gigatable right now. Could be called Gigamap or Megamap or whatever. It is not a database table. It is a Java collection, meaning it has it lives on the client side. It lives in your memory, and it has some features which take away all the work I just mentioned from you. The concept of this collection class is it has an internally segmented structure, meaning we have basically 3 levels of nested arrays which are connected by lazy reference internally. And the entities are internally mapped to an ID, again, like the storage engine does itself. And so only small parts of the needed data is loaded in memory. And you can reach every entity which lives inside the Gigatable by only 2 small lookups, 2 small hash lookups or 2 tiny loads. Even if the collection contains billions of entities, these are always 2 tiny loads. And because the collection can calculate where, depending on the ID, where the entity is sitting, it's always only 2 loads, no matter how big the collection gets. So it can basically scale to infinity, no matter how many entities you put into it. So, and another thing is, what about the searching stuff in this huge collection? Let's say we have millions of entities in them, and I want to filter entities based on some criteria. Do I have to load all the millions or billions of entities in a RAM anyway, like it's now with default collections, because they are searched on the heap, so they have to be loaded first. And then we said we have to add an index for that, and that's what we did. We have various, or the Gigatable itself is an interface which brings a default implementation, and the indices are interfaces as well, meaning we can add multiple index implementations on the go. What we have currently is a bitmap index. The bitmap index lives on the client side as well. It lives it's just binary data, very small, compressed, optimized binary data off heap, meaning it doesn't pollute the heap space and doesn't bother the garbage collector. And if the index gets bigger, the operating system can swap the data to the hard drive. This can only be done if the data is put off heap. It doesn't do it when the data lives on heap, because it's the managed part of the JVM. Off heap is basically just a memory region where you can throw bytes into, and the operating system can swap and reswap the data on demand. So there's probably no way of running out of memory here. So, and the searching now is done in the index, meaning off heap. Basically the fastest possible way on a JVM to search data is to browse bytes off heap, and then depending on the index as result, the data then is loaded internally over the lazy references. And that's how you can optimize the loading in the extreme. So you can pretty much write complete queries down to the last condition, and only the needed entities are loaded into RAM. Basically, like you make you do a SQL query, and that's so you can minimize the data which is transferred on a heap. Besides the bitmap index, we have a prototype for a Lucene index, which can be used for full text searching. It's working pretty well as well. So the Lucene index lives in memory as well, or depending on the Lucene directory you're using on a file system. The bitmap index itself will be persisted in the Eclipse store storage directly. So we have special type handlers for that, so you don't have to worry about anything. You just use the Giga table via API and call the simple store methods, and the index will be persisted in the underlying storage as well. So no worries for that. So how does the code look for this stuff? The Giga table is just an interface which can be created here. Look here, yeah, just say Giga table new and define the type of entity which lives in a Giga table, and then you can define the indices which should be created. For this demo purposes, I created one index for the first letter of the name. So the person has just a name and a date of birth. The first index indices the first letter of the name, and the second one uses the year of the birth date. So the indexes are just it's just a tiny bit of logic which takes the original entity and returns a value which is supported by the index, which is basically every primitive type or number and strings. And then the index will be created depending on the output of the indexer stuff here. So you do that once, and all the indexing, when the index should be updated and so on, is managed by the Giga table itself. And then we can see what happens if you query. The Giga table is persistent. I already put some demo data in it with 10 million persons. And then we fire up a test query, which is a simple Fluent API. You just say, depending on your index, here the first letter should be set of the name, and the birth year should be the year 2000. And when we run the application, we get the result. So we see this condition meets 852 persons. The first 10 or so are shown, and the rest is suppressed. And we see, yeah, the first letter is a set, and it's the persons are born in year 2000. So, and yeah, that's how you can index your data beforehand and lazy load the stuff depending on the condition of your query. And all the lazy loading stuff is done internally by the Giga table. You don't have to worry about where to put the lazy references, how it should be used effectively. It's all done by the table itself. You use it like a default Java collection, if you like, and use the Fluent API of the bitmap index, or you can use if you use the Lucene index implementation, you can use the Lucene query language for that. And depending on frameworks and IDs we will provide different index implementations for the table in the future. And another cool feature of the GigaTable is you don't have to remember what collections you changed to store the right collections. If you use, let's say, 5 maps where you store your entities for different lookups, and you add an entity to all these collections, you have to store all these collections, and that's all stuff you have to think about. And this is error prone. The GigaTable itself memorizes what segments are changed internally. No matter how you manipulate the GigaTable, you only say table store, and the table will take care of the rest and send the right store or the right objects to the storage itself. So it's a very convenient way to manage big amounts of data. The GigaTable is designed to scale in very huge sizes, so we're talking billions of entities here. Because of the segmentation, the lookup time doesn't scale with the entity count. You only have 2 small lookups, no matter how many entities are in the GigaTable. And the query isn't sent to a server application. It's run off-heap in memory in your application, and only the result of the query are loaded into memory from the storage. So it's the most effective way. And if too much parts of the GigaTable is loaded into memory by the lazy loading, the lazy reference manager itself takes care of unloading the stuff anyway. So you don't have to worry about loading too much stuff off the table. And the lazy reference manager will take care of so you don't run into a out of memory situation. All right, yeah, we are really very excited about these features, and some smaller ones which are coming up. One is ready and will be in the 1.1 release. We did some garbage collector optimization, which the garbage collector detects objects earlier and can clean up the storage more effective. So the housekeeping doesn't have to get too much time and block too much processor time. So there's an optimization. And another one is we have some objects or some classes on our blacklist which cannot be stored or serialized, and throwable or exceptions was one of them. But we got a feature request from some users. They say they want to lock or store the exceptions just for logging purposes or for monitoring purposes, and therefore we will provide a type handler for the throwable interface so that exception types can be stored or serialized as well. All right, so that was a quick overview about what we're currently working on. Some of the stuff will be released in the 1.1 release. The 1.1 will become either in December or in January, depending on the tests. There are some modules left which we didn't move to the Eclipse Foundation yet. It's the cache and the implementations for the integrations into different frameworks. We will move this code to the Eclipse Foundation starting now, and the release 1.1 will contain all the missing stuff from the MicroStream or the remaining stuff from the MicroStream framework, which isn't at the Eclipse Foundation. And from then on, the active development will move completely to the Eclipse Foundation, and the MicroStream repository will be in a read-only mode or in a archived state. So it will be accessible, but development will only happen at the Eclipse Foundation.